Our next speaker is Dr. Ouyang, who comes from Georgia Tech, working in Alex Gray's FAST lab, and he'll be speaking about SVN and some non-smooth minimizations. So hopefully this gets going. Let's see.
Can you hear me? Thanks for the introduction, and good morning. Welcome to my talk. And my name is Hua Ouyang, and I'm a PhD student of Dr. Alex Gray, and we are from Georgia Tech. So today I'm going to talk about a new algorithm for the stochastic minimization of the non-smooth functions. Now, for the non-smooth functions, we mean the non-smoothness in the loss functions. So let's start from a very simple randomized algorithm, which is called the stochastic gradient descent algorithm. And the SGD is very popular in lots of communities. People have used it from the 50s. And it is a very simple randomized algorithm. And the machine learners have used it for very large-scale problems. And it was proposed by Robinson Monroe in the 50s. It is pretty old algorithm, but it is descended fast. And there are many variations of SGD. Say, you have proposed the average SGD or adaptive step size SGD, but it turns out that still the classic SGD is still hard to beat. And SGD has been applied to many machine learning applications, such as SVM classification and regression, and signal reconstruction neural nets. It turns out that perception is an instance of the SGD algorithm. The good thing about the SGD algorithm is that it does not need to go through the entire data set. So it is memory efficient, and it is very good for large-scale and sequential data. Another good thing about the SGD is that the theoretical guarantee in SGD is in terms of the expectations. So, despite all these good properties of SGD, it is inherently a black box algorithm. So that means that it does not explore any structure of your problem. The rule of thumb is that if you want to achieve a better result in machine learning applications, the good way to go is just to explore the structure of a problem to the extreme extent. So in this work, we propose a so-called accelerated non-smooth stochastic gradient descent, or NSGD, by exploring the structure of our objective functions. And we give the name ANSGD, but actually it's not an SGD, as we'll see later. And we're sure that it is theoretically and empirically better than all the previous subgradient descent-based algorithms. Now I'll give you a very quick review of the state-of-the-art stochastic algorithms. So the oldest one is the SGD, and it has a very simple update rule. Here, ET is a step size, and this is a subgradient if your function is non-smooth. And another one is the recently proposed stochastic dual averaging, and this method is essentially has a pretty much similar performance as the SGD. And also, you have used the average result of the previous solutions to do the final prediction, and this is called average SGD. It's also good enough under some assumptions. And another thing is the ACSA is the accelerated stochastic approximation recently proposed by them. This method utilized Nonsmooth's accelerated gradient method, and it was originally proposed for smooth functions, but actually it can be used for minimizing non-smooth functions. But I need to mention that for all these methods, if you want to use these methods for the non-smooth minimization problems, and I mean for minimizing non-smooth loss functions, you have to resort to using subgradients. Now, there are some lower bounds here shown for these stochastic optimization algorithms. And this bound is the lower bound for the for minimizing general convex functions, and this is bound for minimizing the strongly convex functions. But actually, these two lower bounds are not very interesting because it does not distinguish the estimation error from optimization error. And also, these two bounds are of the same order as the lower bound of the estimation error. So we'll see that it turns out that the constant here really matters. And or you can just have a fine-grained bound, which is a sum of two parts. One is the estimation error, another is the optimization error. And we'll see that for all these subgradient descent-based algorithms, the optimization error is still of the same order as the estimation error. And it is by our smoothing method that we can just accelerate the optimization error to a faster rate other than the slow rate of the estimation error. We'll give some detailed discussions about this in the next several slides. So the key ingredients of this work are two things. One is the stochastic setting, another thing is the non-smoothness. So first, I'll talk about the stochastic optimization view of machine learning. So from a frequentist point of view, supervised learning is like minimizing some kind of a expected loss function, and this task is the subtask of the stochastic optimization. So for the optimization community or stochastic optimization community, people have proposed two general classes of methods for solving stochastic optimization problems. One is the sample average approximation SAA, and actually this is to minimize the empirical risk function, and it's almost the same as the so-called batch learning. And second thing, the second method is called stochastic approximation, which we are adopting in this work. So actually, this method directly minimizes the expected risk function by taking the samples. So SGD is a kind of instance of this stochastic approximation, and the online learning or online convex optimization is algorithmically related to this SA. So a general idea here is that, as shown by the two, the generation error that we care about can be decomposed into three parts: approximation error, estimation error, and optimization error. So if we have a fixed model, then we have little control about the approximation error. So we need to care about the trade-off between the estimation error and optimization error. The good thing about this stochastic approximation is that the guaranteed theoretical guarantee of SA are in terms of the sum of these two terms. Now, let's come to the other ingredient of our work, that is the non-smoothness in our object functions. So actually, in machine learning, many problems can be boiled down to non-smooth minimization problems, such as, for example, if you are focusing on the empirical risk minimization, which is the sum of a empirical loss function plus some regularization term, you can see that both of these two terms could be non-smooth, but both of them are convex, but both of them could be non-smooth. For example, for the loss function f, the hinge loss, absolute loss, absolute intensive loss are all non-smooth. And for the regression part, the one norm, infinite norm, group Russell, or nuclear norm are non-smooth. So you might ask, why bother using non-smooth functions? The answer is that it has many favorable properties. For example, in hinge laws, it can lead to very sparse SVM classifiers. And people have shown that hinge laws is statistically better than any other smooth loss functions for classification tasks. And also there are many other favorable properties. But the question here is that the problem here is that the non-smooth optimization is inherently hard. It has been proved by Mimirowski that in the worst case, the iteration complexity of minimizing non-smooth functions, for minimizing general non-smooth functions, could be order 1 over epsilon squared, meaning that it has a very slow rate of 1 over root t if you run your algorithm for t iterations. So it is generally hard, but if you have a very good structure in your object function, then it will give you some hope. Now the question here is that what kind of favorable structures we want to explore? As we mentioned before, SGG does not explore any structure in your program. It just depends on the first order information that is subgraded in the object function. So we are focusing on the sum of the loss function and the generation term. So if you want to explore the structure in the generation term, there has been lots of work on that, assuming that your regression term has a very simple form. So this technique is called splitting or composite setting, and the idea is to minimize the first order approximation of your loss function plus a recommended divergence plus the very simple and structured non-smooth regression term. But this method relies on the assumption that your loss function is smooth. But what if your loss function is non-smooth? So our assumption here is that we are hoping that our loss function has a very nice equivalent convex concave set point form of this one. Here, U is an auxiliary variable. So there are many examples showing that the machine learning applications can be turned into this form. Say, for example, the minimize the maximum of L functions can be turned into this set point form, and minimizing the D norm regression problem can be also turned into this form, subject to the constraint that U is constraining the dual norm. So we have made the assumption that our problem can be turned into this set point form. But what's the benefit of using this set point form? Now, there are several answers to this question. So Mimirowski's answer to this question is that we assume that the set point function is smooth with respect to x with fixed u, and it is smooth with respect to u with fixed x. So based on this assumption, we can use the so-called saddle point mirror descent to achieve a faster rate than the subgradient descent methods. Another answer to this question is the Nastrov's deterministic smoothing method. And this method assumes that we can approximate our equivalent set point form by a smooth function, a smooth approximated function of the original function. And we assume that the approximate function is simple to solve. So in the machine, as we have seen before, in many machine learning programs, the non-smooth losses can be turned into this set point form, and we can have a deterministic smoothing of our loss function. So here, this equation gives the gives the definition of Nesterov's deterministic smoothing. You can see that without this term, the first two terms are equivalent to the original loss function. And it is with this term that we can have a smooth approximation of the original loss function f. And the intuition here is, okay, here omega is a strongly convex non-negative function, and gamma here is called a smoothing parameter. It's non-negative smoothing parameter. So the intuition here is that gamma should be a very small number, such that the approximation is not far away from the original function. Now, the limitation of this method is that one has to know the number of iterations you want to run beforehand. And this is not suitable for stochastic programming or online learning. Well, you do not need how many number of iterations you want to run beforehand. So based on this intuition, we propose a stochastic smoothing of our loss function. And this is the definition of the stochastic smoothing. And you can see that it only differs from the deterministic smoothing in two parts. One part is the linear operator A here, and A here is a stochastic term, and it is related to your sample psi t. And another thing is that it has a time varying smoothing this parameter gamma t. And both of these two terms change with time. So as we will see that it is very crucial to find a proper series gamma t to ensure a fast rate of convergence. Now, these two. Now we give some properties of this smoothness approximation. So, all right, I'll skip this one and go back to the directly to the axiom. And this axiom is actually a direct application of the Nesterov's accelerated gradient descent together with our stochastic smoothing. And you can see that the line 1, 3, and 4 are almost the same form as the accelerated gradient, but and it can be simplified to a equivalent but simpler axiom. So here is our main result, and the interesting part is if here we have the 1 over t bound for the non-smooth part. And for the strongly convex function, we can have the asymptotically you can have 1 over t squared bound for the non-smooth part. So here we compare the bound for of NSGD with ACSA and SGD. You can see that the third term here are the estimation errors, and for these two, the non-smooth part is the same order as the estimation error, but for our axiom, it is faster than the estimation error. And also, it is the case for the strongly convex cases. It is the order 1 over t squared other than 1 over t. So as a byproduct, we have shown that we have proposed a batch to online conversion. And here are some examples of the smooth approximation of the hinge loss and the absolute loss. Here, the approximation are the lower bounds of the original loss function. And we have shown empirical results comparing with the average SGD and the original SGD, and it outperforms these two subgradient descent-based axioms in most of the data sets we have chosen. And the only exception is this data set, is the data set alpha. And it has a higher function value, but it has a contradictively lower testing accuracy. Maybe it is due to the incomplete optimization, and it cannot be predicted by our theory. And also, we compare our axiom with the state-of-the-art ACSA axiom, and we can see that it outperforms the ACSA by a large margin. And okay, I think that's the end of my talk. And I'll leave time for questions. Thank you. Huh? All right. So the conclusion here is that we have extended our, we have introduced a different complex setting. We are focusing on the non-smooth loss, minimizing the non-smooth functions other than the non-smooth regularization term. And we have proposed a very simple stochastic smoothing method, and together with the Nestorov accelerated gradient, we propose the NSGD. And actually, this actually achieved nearly optimal rates under both convex and strongly convex assumptions of your loss functions. And as a byproduct, we propose a batch to online conversion, and we can show that almost any good stochastic algorithm can be used for online learning. And there are several ways to extend our work. Try to extend to constraint minimizations, and we try to find more interesting and harder applications. And also we try to solve problems where the approximate function is not easy to solve in a closed form. And also we are thinking about parallelize the NSGD and what is the optimal mini batch size. Then maybe we can step aside the NSGD using simple average, like an averaged SGD have done. Right? That's the end.
Okay.
Thanks.
So let's take questions.
So this averaging always seems to help. Have you ever played around with sort of decaying averaging, or where you take the recent ones at higher weight?
I didn't done experiment on that, but the simple averaging over all the previous solutions give a pretty decent solution, which is the average SGD that we have seen in the experimental results. The green line is the average SGD. It is decent. It is pretty good, close to our solution. Yeah.
So could you go back to your main theorem, please?
Yeah.
Okay. So you seem to suggest that because you're taking advantage of the structure, you're able to go past what the lower bound suggests.
Yeah.
Which seems kind of inaccurate to me, because the lower bound that you refer to actually have a sigma over root t lower bound that they prove, which is exactly what the upper bound you're proving here. So I'm unable to see how you're going past the lower bound.
Okay, let's take a look at the comparison here. The SGD has 3 terms.
That's an upper bound. That's not a lower bound.
Yes, exactly. But my argument here is that the lower bound is not really a tight lower bound.
Your algorithm is not going any further than what the lower bound can be, right?
Yeah.
It's sigma over root t,
sure.
Which is what you're showing there. So
we are not claiming that we can do a 1 over t other than 1 over root t here, because this is the dominating part, right? This is the estimation error, right? But we include this 1 over root t to 1 over t. This is the key contribution of this work.
Right, but that term is not present in the lower bound at all. So for all we know, that term might not even need to be there at all.
Mm-hmm.
So in some sense, you're not beating the lower bound in any way. You're still worse off compared to the lower bound, and it would be theoretically very problematic if you were able to actually beat the lower bound.
Well, my answer is that this is the lower bound for estimation error, and there must be a lower bound for the optimization error. Right.
We can take it offline. The lower bounds are for optimization
sure.
error.
All right. Okay. Let's check offline. Thank you.
Any other questions? Okay, let's thank the speaker again.
Thank you.
Time for coffee break. We'll return.
The machine learners have used it for very large scale problems. And it was proposed by Robinson Monroe in the 50s. It is pretty old algorithm, but it is decently fast. And there are many variations of SGD. Say if you have proposed the average SGD or adaptive step-size SGD, but it turns out that still the classic SGD is still hard to beat. And
Let's see.
The Nonsmooth functions will mean the Nonsmooth in the loss functions. So let's start from a very simple randomized algorithm, which is called the stochastic gradient descent algorithm. And the SGD is very popular in lots of communities. People have used it from the 50s. And it is a very simple randomized algorithm. And no, can you hear me? Thanks for the introduction, and good morning. Welcome to my talk. And my name is Hua Ouyang, and I'm a PhD student of Dr. Alex Gray, and we are from Georgia Tech. So today I'm going to talk about a new algorithm for the stochastic minimization of the non-smooth functions. Now for the
next speaker is Dr. Ouyang, who comes from Georgia Tech, working in Alex Gray's FAST lab, and he'll be speaking about SVN and some non-smooth minimizations. So hopefully this gets going.